None of us want a house that looks like this one. The proud builders of this house failed to do a permafrost investigation, and within a short time after completion, the owner's dream home became a nightmare. In interior Alaska, there is no way to tell for sure if your house is on non-thaw-stable permafrost without doing a permafrost investigation. In the next 20 minutes, we will discuss why we do a permafrost investigation, when we do a permafrost investigation, how we do a permafrost investigation, and how you evaluate the results of a permafrost investigation. Let's talk about the first topic, why we do a permafrost investigation. No one wants their dream home to end up like one of these and their life savings to sink into the ground. The consequences of building on non-thaw-stable permafrost and not knowing it are serious, and there is no way to tell for sure what is under the ground from the surface. The term permafrost refers to ground that is continuously below the freezing temperature of pure water. Permafrost may be thaw-stable or non-thaw-stable. Relatively dry permafrost is thaw-stable for home construction and will not present a serious problem if it is thawed. Relatively wet soil may be non-thaw-stable and cause disastrous differential settlement if it thaws under a house. In general, construction will cause a warming of the ground and thawing of permafrost, unless precautions are taken to reverse the trend. Let's go to the permafrost tunnel near Fox and take a closer look at permafrost. In the tunnel, we have a unique opportunity to go underground and see permafrost up close. The tunnel is owned by the U.S. Corps of Engineers Cold Regions Research and Engineering Laboratory. Note the types of vegetation over the tunnel. We will discuss this later. Now we're about 40 feet below the ground surface, looking at the ice formations in the walls of the tunnel. Ice looks dark in the photographs. This is an ice wedge. Ice wedges are formed by water running into cracks in the earth in the spring and freezing in the permafrost. Ice wedges grow to 15 or 20 feet deep and can spread laterally until the tops touch. Look above the ice wedge and you'll see a buried pond. Ice masses, such as frozen ponds and river ice, frequently get buried and remain frozen in the permafrost. Now look at the wall and see the buried lake. This lake could be a few feet deep and a few yards across, or it could be many acres and tens of feet deep. The scary part is that there is so much variability from place to place. A boring drill to the left side of the screen would completely miss the major ice features which are clearly present. These ice lenses were formed by frost heaving the last time this ground was frozen before it was buried. Ice lenses can be so thin that they can't be seen with the naked eye, or many inches thick. Ice lenses are clearly potential problems if they thaw under a house. But how about frozen soil? Frozen soil can look dry, feel hard, and still be non-thaw-stable and settle a great deal when thawed. Now that we see how important it is to know whether or not there is non-thaw-stable permafrost under the house, let's discuss when we do a permafrost investigation. The rule is very simple. A permafrost investigation is necessary any time construction is considered in an area where there might be non-thaw-stable permafrost that could adversely affect your construction. If a house was constructed without a permafrost investigation, then you are taking a very big chance if you do not do one before you become involved in any way. It may be many years before problems show up, so just because the house has not shown signs of distress in the past several years does not mean that it will not show distress next year. The next obvious question is there any way to look at a site and tell if there's non-thaw-stable permafrost? The answer is maybe. There's an old saying that permafrost does not exist where there are birch trees. Let's revisit the permafrost tunnel. Do you see any birch trees over the tunnel? Do you remember what kinds of trees surrounded the house in the opening scenes of this video? Just in case you don't, here it is again. There is but one type of vegetation which clearly indicates that there is no permafrost in the area. That's right, palm trees. There are also other advantages to living around palm trees, but then that's another story. Seriously, there may be thaw-stable permafrost anywhere the weather conditions are right. On the other hand, it is well known that black spruce trees indicate the presence of permafrost. Granted, in interior Alaska, the area is most likely underlain by permafrost in areas where the black spruce are prevalent, but this is not true in other areas. For instance, black spruce trees in Anchorage usually indicate a peat bog. This map from the Environmental Atlas of Alaska was developed at the University of Alaska Fairbanks. It shows Alaska divided into 4 zones, generally underlain by continuous permafrost, underlain by discontinuous permafrost, underlain by isolated masses of permafrost, and generally free from permafrost. From this map it appears that Fairbanks is in an area of discontinuous permafrost. That is, we may or may not have permafrost at any given location. Nome is underlain by continuous permafrost. Anchorage may have isolated masses of permafrost, and Juneau doesn't have permafrost. There are more specific maps in many local government offices. At this juncture, it is critical that we have local expertise at our fingertips. Knowledgeable local people probably have a fairly accurate view of whether there's permafrost in a given area or not. Now that we know when to do a permafrost investigation, let's find out how we perform the permafrost investigation. The first item of business is to find out as much as possible about the area from local experience. Look at the surrounding structures, talk to the neighbors, and talk to local experts. Never rely completely on what you're told, but consider it all in your final analysis. The seller is not usually the best source of information. Next, visit the site and look for signs of permafrost, including at least the following: thermokarsts, drainage, vegetation, slope, elevation, snowfall, and shade. Thermokarsts are holes or depressions left in the ground when ice or non-thaw-stable permafrost thaw. This view of the Fairbanks Golf and Country Club shows classic examples of thermokarsts in the form of depressions. If the depression was not made by man and is not an erosional feature, it is likely a thermokarst. These holes are made by thawing ice masses. There is likely a large void under the ground, and only a small part of it is visible. Drainage is important to site development as well as finding permafrost. Poorly drained sites tend to be slightly cooler and hence have a higher likelihood of having permafrost under them. In addition, drainage that ends strangely may be falling into an underground cavity formed by thawing ice. Vegetation is an indicator of the existence of permafrost, but the indicator changes from location to location and is not absolute at any location. Here, in the Goldstream Valley, it is likely that there is permafrost under the areas covered by the spruce trees, and there is not permafrost in the areas covered by the deciduous trees. Generally, dense vegetation like moss and tundra are indicators of cooler temperatures and permafrost in some areas. The slope is important for several reasons. North and east-facing slopes are shaded in the winter and don't get direct sunlight in the summer and therefore are cooler. Steep slopes tend to be better drained and accentuate the trends. On a regional basis, higher elevations are generally colder, usually on the order of 3 degrees Fahrenheit per 1,000 feet. Locally, however, cold may settle into the low spots, causing a temperature inversion. In some areas, the low spots are therefore the coldest, partially because of the drainage and vegetation, but also because of the temperature inversion. The ground in areas of high snow accumulation will be warmer because snow acts as insulation and protects the ground from the cold above. Areas of higher snow accumulation are usually cloudier also, and therefore are generally warmer in the winter. Shade causes cooler temperatures, particularly in the summer. Shade can be created by dense vegetation, steep terrain, or adjacent construction. If it is necessary to determine if there is non-thaw-stable permafrost under the site, it is absolutely necessary to do some form of subsurface exploration. This is usually done with a drill rig, but can under some conditions be done with a backhoe. This drill rig, provided by Shannon and Wilson, has a hollow stem auger. Mike Lekorchek will describe the drilling and sampling process.
This drill rig is a CME 55. Its primary function is for drilling geotechnical soil samples and doing for foundation design for buildings and things, rock and mineral prospecting. What we're going to do today is take a couple of samples out of the ground, different types of samples. The first thing we're going to do is drill down with this hollow stem auger. It's a continuous flight hollow stem, has a 3 1/4 inch inside diameter. We'll drill down to about 5 feet, pull the center out, and we'll drive a split spoon sample and get a sample of the ground from 5 to 6.5 feet. Then we'll drill down a little bit further. We know that in this area we're going to hit in frozen fine-grained material, and we'll take another sample that will be dry core. We're going to start drilling now. That the plug at the bottom is just to hold the center of the hole open till we get started. And we'll retrieve that out of there and leave the center open with just a split spoon in it. This is the split spoon sample that we'll be driving. It's a 2.5 inch inside, 3 inch outside diameter. We use these around here because of all of the heavy gravels. This is the drive shoe, sample catcher, and then to extract the sample we just open it up in half. We'll put this in the ground. We'll drive this 18 inches with a 300-pound hammer. We'll count the blow count that it takes to drive the spoon for the 18 inches. We'll count the blows for every 6 inches. They've drilled down to about 4.5 feet right now. They're going to drive the split spoon out the end of the auger into the soil, and then we'll pull the sample back and take the sample out of the spoon. We've marked the rod off in 6 inch increments. We're going to drive the spoon the 18 inches, and we'll count the blow counts that it takes to drive the spoon each one of those marks. Now, this is a 300-pound drop hammer. We'll be dropping it 30 inches onto the rods to drive the split spoon. Broke through the frost, looks like. Now we'll pull the split spoon back up out of there. We'll extract the sample from it. This is the sample we just drove. You can see all the ice in the end of this. This is frozen. It's all frozen cinders and peat. It's got a real high ice content. See all the ice lenses. If it should thaw out, all that ice will turn to water, and there'll be a void there. The water can drain out of the sample. And what we're going to do is drill this pipe down into the ground. It's actually a BW core barrel, and it's a single tube. It's got a special bit on that we make for this. We'll get a 5-foot length of soil, a continuous sample out of the hole. We can get a better look at how much ice is in it. This is the bit on the dry core barrel, and what it actually is, these are pieces of rough carbide on here, and they will cut the soil and allow the core barrel to go down. We're going to do this dry coring. It'll go fast enough that we'll only melt the ice around the outside of the sample. The inside of the sample will stay frozen and intact. We'll get a little bit of a thaw drying on the outside, but not enough to bother with. It will still have a good sized sample of the frozen material. Okay, what we're going to do now is extrude the sample from this core barrel. And the way we do it is we've got a hydraulic press on the side of the rig, and we just push the sample right out the end. This is, as you can see here, is peat. some of which is thawed and has no strength to it at all. And down here where it's frozen, we'll cut it open and take a look, see how much ice is in it. You can see it's frozen, and you can see the ice is starting to melt inside of it. You can see the ice lenses all through here. This is pretty firm right now, but when it thaws out, it'll be just like this. There's no strength to it at all. Clean some of the rind off the outside of this so we can get a better look at the sample. We've got some larger ice lenses in here. Now here's a real large ice lens, goes from here over to here. You can see it's just about a ½ inch thick. It's all ice.
The results of the subsurface exploration are shown on the boring log like this one. Almost everything you need to know about a permafrost investigation is shown on the boring log. Probably the item of most immediate interest is whether or not the ground was frozen. A black bar running along the graphic log indicates frozen ground. Equally significant is the completion date of the boring. The time of year tells a lot about the seasonal frost, while the year is significant because the thermal state can change with time and old borings are not necessarily representative of conditions at the present. The graphic log indicates the type of material at a glance. Always look for the blanks. They indicate clear ice. More detail is shown in the soil description next to the graphic log. After the soil description may be some random letters which form one or more classification systems. The letters after the soil description tell a lot about the soil. There may or may not be a thawed ground classification, but if the ground is frozen, there will always be a frozen ground classification. The frozen ground classification system generally used was developed by Linell and Kaplar from Purdue University in 1963. It is used extensively to classify permafrost. The capital N means the ice is not visible. The following, F or B, indicates whether the material is friable or bonded. If the soil is friable, it is most likely thaw-stable. If it is bonded, there may be excess ice or no excess ice, as designated by the E or the N. If there is no excess ice, then it is also likely thaw-stable. But if there is excess ice, it is likely that it is non-thaw-stable. If there is visible ice, the classification will start with a V and be followed by another letter, depending upon the texture of the ice. If there is any visible ice, it is almost certain that the soil is non-thaw-stable. If there is visible ice, the ice will be classified. X is for crystals, C is for coatings, S is for stratified, and R is for randomly oriented ice formations. The percentage of ice in the soils is estimated whenever possible. The percent is based on visible observations, and although it is significant, it is not precise. Back to the boring log now, we find several other things of interest. The location and type of samples is very important. There is very little information between samples, and the type of sampler indicates the quality of the sample. The single line indicates a drive sample, which results in a disturbed sample of soil, whereas the three vertical lines indicates a coring, which gives a nearly undisturbed sample. If water was found, it will be designated by a triangle with the date of the observation under it. The date is important because the water table varies from year to year and throughout the year. The elevation might not be representative of other times and other years. Over here is a graphic depiction of the water contents and the number of blows required to drive the split spoon. The blow counts are designated by triangles and are used to determine the competency of thawed materials for foundation support. The blow counts may also help determine if dry soils are frozen or thawed. The water content is designated by a circle. It is the ratio of the weight of water to the weight of dry soil in a unit volume. The first evaluation of thaw stability is made by comparing the soil description to the water content. There are combinations that are representative of materials that are thaw-stable, and there are other combinations that are indicative of materials that are non-thaw-stable. Frequently, the soils will obviously be in one of these two groups, and the evaluation of the soil is complete. If the soil falls into the questionable range between these two zones, then additional work would be necessary to continue with the design. The contractual obligations for a normal permafrost investigation stop at this point, with an estimate of the stability of the questionable materials and a short comment about what the materials found indicate about the stability of the materials across the whole site. If the evaluation of the site is that it is questionable, it may be most economical to continue the study with laboratory tests, additional borings, and engineering analyses. Wouldn't it be great if we could look into the earth from above and tell what's down there? There are a number of techniques available to do just that. They're called geophysical methods because they measure differences in the physical properties of the earth. Many of them do this quite nicely. The problem arises in trying to interpret what the changes in physical properties mean to a house built on the ground surface. There are 4 geophysical methods in common use today for foundation exploration: seismic refraction, electrical resistivity, ground-penetrating radar, and electromagnetic energy transmissibility. Each of these geophysical methods do what they claim, but today none of them can be used alone to determine if the material under the surface is thaw-stable or not. There is considerable precedent for using these techniques to determine variations within materials between borings, but this is beyond the scope of most permafrost investigations for homeowners. There are several laboratory tests which are used to evaluate the stability of a site. All of the analyses are directed towards determining the density of the soil as it is in the ground, and the density of the soil after it has been thawed under the imposed load. Thawing soil is typically very loose, so further testing may be necessary to determine the effects of vibrations, such as earthquakes. After the subsurface explorations have been made and the laboratory tests have been performed, it is necessary to interpret what the available data means about the stability of the site. If you'll remember the permafrost tunnel, it is obvious that conditions elsewhere on the site may be significantly different from those at the point of exploration and sampling. The permafrost investigation may or may not include a summary statement. Let's summarize the permafrost investigation. In order to avoid this, you have to check with local experts, look carefully at the site, perform a subsurface exploration, do some laboratory tests, and remember the variability. If the site is not underlain by non-thaw-stable permafrost, proceed. If the site is underlain by non-thaw-stable permafrost, design for those conditions. If you're not sure, either do more exploration or design for the worst case.